Assalamualaikum and good morning. Well, hello everybody. How are you guys doing? I hope all of my students in good situation for this whole MCO period. So we hope that this COVID-19 situation will improve soon. So uh, regarding our chapter 2, which is a Fourier series, actually we are at the end of this chapter. Okay, we only have to cover the last topic under this chapter. So before we proceed, I believe it's a good idea for me to have a quick revision to all of you. Okay, so at the early of this chapter, I have explained the importance of the frequency domain. Okay, besides the time domain. Okay, I explained to you who is this guy, Joseph Fourier. Okay, and what is his famous statement? A non-sinusoidal periodic function can be expressed as an infinite sum of sinusoidal functions. Now I believe all of my students understand what does it mean by his statement, and I have give you the concept. I have explained in this diagram the concept of the Fourier series. Okay, you can look that if we uh, made a summation of the fundamental frequency, okay, with the many frequency component, okay, of the next harmonics and so on. Actually, when we combine it, we can generate a, a non-sinusoid periodic signal, right? So this is the second example. Right, next. Okay, the definition of the Fourier series. Okay, after we have looked to the concept, next we jump to the mathematical equation. Okay, so this is a trigonometric Fourier series. Ft equal to a naught plus summation of an cos n omega naught t plus bn sin n omega naught t. This is the DC component, and then this is the AC component. And then I have explained to all of you the importance of the coefficient. We need to find the A naughts, AN, and BN. So what is the difference between A naught, AN, and BN? I have explained many times to all of you. The A naught, which is DC component, which will raise your periodic signal, while the AN and BN will help to shape your non-sinusoid periodic signal. Okay, so next we have looked to the one of this example. Okay, from there we have to calculate the A naughts. The formula is given, so this formula you have to memorize it. The coefficient of A naughts, and then you have to calculate the AN and BN. From there you get the mathematical equation that represent of that non-sinusoid periodic signal. From there, we can plot the amplitude versus the frequency and the phase versus the frequency. So we can look the difference from the continuous and periodic signal in time domain, and after it change, we plot it in frequency domain, the behavior signal has changed. Okay, then we summarize it into this one. In time domain, this is continuous in time periodic signal, which represented by st. In frequency domain, it is discrete in frequency, which is a non-periodic. Next, okay, I have explained about the Gibbs phenomenon. Okay, about the symmetry condition. There are three types of symmetry. even, odd, and halfway symmetry. So why is it important for you to determine the symmetrical of your signal? It helps you to simplify your calculation. So you don't need to calculate all of the coefficient. If you get the odd, your A0 and AN is equal to 0. So you just have to calculate the BN. Right? This is the even symmetry I have explained to you. It's a mirror at the y-axis, and then you can look at the formula for the even symmetry. The A naught equal to twice than before. Now we have 2 over t, 2 over t, and then your integration is from 0 to only half of the cycle ft dt, and then the an is equal to 4 over t, integration from 0 to half of the cycle ft cos and omega naught t dt, and bn is equal to 0. Okay, for odd symmetry, a naught and an equal to 0, and bn equal to 4 over t, do not confuse, right? And your integration from 0 to t over 2, right? Okay, we have discussed about half-wave symmetry, but I didn't emphasize on this. As long as you still remember about the even and odd, that is a great help, right? So when you get a periodic signal, first of all, you should determine the symmetrical of the signal. Okay, whether it's a odd symmetry or even symmetry. Okay, and then I will explain about the idea of the exponential Fourier series. Skip this. Right. Okay, our last class is on this topic. It is about the application of the Fourier series on the circuit application. In this case, if you have a periodic signal, whether it's a voltage or current source to your linear network is a R, LSC, and component, right? So we can apply the Fourier series concept here, right? Okay. All right. Okay, that's all that you have covered. Okay, before we enter the MCO period of time. Okay, so our last topic will be average power and RMS. Okay, this topic I will explain it in the next video. Thank you.